All right, guys, so we are now recording. So let me go ahead and share my screen and to go over with you guys what is in Schoology and explain to you guys what is going on today. All right. So okay, so in Schoology, you're gonna click on courses and you're gonna click on fourth period. Oh, and by the way, I want to let you guys know that as we close out the end of the school year, for those of you guys that took the AP test, you guys will not have to take the final exam. You are exempt from the final exam. So that was basically the overwhelming majority of you guys because they gave me a list of everybody who showed up to take the AP exam, and most of you guys showed up. I think it was about like 10 or so students that didn't show up. So if you did not show up to take the AP exam, I'm going to be getting with you guys later on in the week to discuss what you guys need to know for the final, or what you guys need to do, or what you guys are going to be doing for your final exam. So I'm going to discuss that with you guys later on. But the overwhelming majority of you guys are exempt from the final exam because you showed up to take the AP test. Um, and of course, the AP test, those scores will not be back until July. July is when those scores will be back. Now, obviously, as you guys know, it was a very difficult test. The AP exam, especially the AP exam, is very difficult. In fact, they curve the test every year because it's so fast, because it's so difficult. I'm personally hoping that the College Board will do a bigger curve this year than they've done in the past, simply because this was a very weird year for most AP teachers. But we'll see. We won't know until July. Um, so just to let you guys know that again, if you took the AP test, you are exempt from the final exam. Okay, so if you click on fourth period, you click on materials. Okay, so there's a folder for today, or there's a folder for this week. This folder right here, and of course today is May the 17th. And it is a Monday. Okay. So on today, we're going to be talking about waves and oscillations. We're going to go over some notes, go over a few examples, and then I'm going to release you guys to do this assignment. So if you pay attention today, you guys should be fine on the assignment. Okay. So thank you, Angelina, for dropping that attendance form. Okay. So let's go ahead and look at this now. I want to begin by reviewing some concepts. But before I do that, I want to pull up that PDF file from Schoology. I'm going to pull it up in Kami so that I can annotate it. Now, as we talk about waves on today, waves involve something that is known as harmonic motion. What exactly is harmonic motion? Well, harmonic motion deals with modeling processes that repeats themselves over and over and over again. So if you have some sort of motion that is repetitive and it repeats itself, we call that process harmonic motion. Let me show you guys a few examples of things in nature that show us harmonic motion. Consider this example right here. Okay, so imagine that you had a block attached to a spring, and you pull that block back and you release it. So as it attached to the spring, that block is going to sway back and forth, back and forth, back and forth. This is an example of harmonic motion because notice we see a process that's repeating itself. In this case, the block is just swaying back and forth over and over and over again. It's repeating itself. Now, we're not going to have time to talk about the kinetic energy and the potential energy of this oscillating system. We're not going to get into that much detail with that this year because obviously we're not going to have enough time since we only have 2 weeks left in the school year. But I just wanted to show you guys what an example of harmonic motion looks like. So this is an example of harmonic motion. And of course, assuming there's no friction here to dampen this system, this block and this spring is just going to keep swaying back and forth, back and forth, back and forth without end. So this is clearly an example of harmonic motion. So any process that repeats itself over and over again can be modeled mathematically as a harmonic oscillator. Now, we've actually talked a little bit about harmonic motion in the past, and you guys didn't even know it. For example, back in our circular motion unit, we talked a little bit about harmonic motion in the sense we talked about period and frequency, which will be terms also important to this unit as well. So, I want you guys to think back to our circular motion unit. So if you guys remember, I showed you guys this clip of a Ferris wheel back when we talked about circular motion. Guys, this is also another example of harmonic motion. Anytime you have something moving in a circle and it just keeps moving in a circle, this is an example of harmonic motion because this is a process that is repeating itself over and over and over and over again. So it just keeps moving in a circle. So this is an example of harmonic motion. Now, I want you guys to remember, whenever we're talking about harmonic motion, there are two important terms you guys to know, and that is period and frequency. So, can someone tell me, do you guys remember how we find the period of the Ferris wheel here? What exactly is period? Anyone want to tell me, chat box, how do we find the period of the Ferris wheel? Anyone remember? Well, what is period? Can someone tell me? Anyone want to put it in the chat box? I know we talked about this a while back, so come on, guys. Anybody remember?
Does that have something to do with time?
It does have something to do with time, exactly. What does it mean? The time for what?
Like when it, like the time, like when the Ferris wheel does like a circle,
Yes.
something like that.
Yeah. So the time for one cycle. Yes, that's what period means. Period means the time for one cycle. So, for example, guys, right now I have out my cell phone, and on my cell phone, I'm going to pull out my stopwatch. So I have my stopwatch on my cell phone. Guys, if y'all see this yellow box here, I'm going to wait till the yellow box come all the way around to the top, and I'm going to press start on my stopwatch. So when it comes down to the very top, I'm going to press start. So now. Okay. So when that yellow box comes all the way back around again, I'm going to stop my stopwatch. Okay, stop. Okay, so guys, my stopwatch right now reads 13.9 seconds. Okay. So in this case, 13.9 seconds is my period. And yes, as Angelina said, it is the time for one cycle. So guys, that is what period means. Period just means the number of seconds in one cycle. So someone tell me, if I know the period of my Ferris wheel, how can I find the frequency of my Ferris wheel? Anyone? Anyone remember?
Do you have to multiply something?
No, not multiply. Think again.
Divide?
Yeah, divide. Exactly. What am I dividing?
The period by something.
Yeah, you do. Basically, it's 1 divided by the period. Yeah, so it's 1 divided by the period. So you're going to take. So in order to find the frequency, we're just going to take 1 and divide it by 13.9. So yeah, you guys were thinking about the right thing, Angelina, Jeremiah. So 1 divided by 13.9. When I do that, that gives me 0.07 hertz. Remember, the unit for frequency is in hertz. The unit for period is in seconds. So I need for you guys to remember that period and frequency are reciprocals of each other. Period refers to the number of seconds in one cycle, whereas frequency refers to the number of cycles in 1 second. Okay, so just something I need for you guys to remember. Something I need for you guys to keep in mind, because period and frequency are two terms that appear a lot in the waves and oscillation unit. Okay, so with that said, let us go back to those notes. So now that we understand what harmonic motion is, let us get into detail when talking about mechanical waves. What are mechanical waves? Well, notice what it says here. Waves combine both harmonic motion and linear motion. Okay. Let me give you guys an example of a wave that combines harmonic motion and linear motion. Consider ocean waves. So if you guys look at ocean waves as they move, so we get two components. Notice an ocean wave travels. So in this case, the ocean wave will be traveling from left to right. But at the same time that the ocean wave is traveling, at the exact same time it's moving linearly, if you look at the top of the wave is also bouncing up and down. So we have motion that's repeating itself combined with linear motion, combined with some sort of travel in a particular direction. So waves combine harmonic motion with linear motion. So in other words, waves involves processes that repeats themselves. Okay, guys, whenever you're talking about waves, okay, in this class, there are two main types of waves you guys need to be aware of. There are two main types of waves you guys need to be aware of. You guys need to understand what exactly is a transverse wave, and you guys need to understand what is a longitudinal wave. So, transverse waves, these waves involve vibrations that move perpendicular to the direction of wave propagation. For a longitudinal wave, these involves vibrations that move parallel to the direction of wave propagation. In other words, the direction of wave motion. So let me just show you guys an example here of these two types of waves. It's better to just see it. Okay, guys, in this particular example right here, I want you guys to notice here that this guy right here has his hand on a long slinky. So guys, for this example, I want you guys to see what a transverse wave looks like. So, and look carefully how he's swaying his hands. So this here will be an example of a transverse wave. Okay, so we're producing a transverse wave in the slinky. Kind of look at that as slow motion. So that's a transverse wave. Okay. I want you guys to see how that differs from a longitudinal wave. So the longitudinal wave looks like this. Okay, so it's a difference. So this is the longitudinal wave. Okay. We're going to watch it in slow motion. So y'all see the difference between the longitudinal wave and the transverse wave? Okay, so for the transverse wave, our vibrations were perpendicular to the direction of wave propagation. In the longitudinal wave, our vibrations move parallel to the direction of wave propagation. What is it that I mean by this? Well, guys, look closely here at how the guy is moving his hand. Okay. So think about this for a second, guys. For the transverse wave, as the guy moves his hand, he's going to send a pulse of energy that travels through the slinky. In this case, the pulse of energy starts right here, and it travels from this end of the slinky all the way to that end of the slinky. Okay, so the energy itself is traveling this way. So the energy is traveling this way. Okay. But guys, look how he's swaying his hand. Notice how he sways his hand in this direction, and then he moves it back in that direction, and he just keeps swaying his hand back and forth like this. So the point is, in order to make a transverse wave, notice how he's swaying his hand. The vibrations of his hand, they are perpendicular to the direction that the energy itself is moving. So the wave energy is moving from here to here, but he's swaying his hands from here to here. So that's a transverse wave. Notice that's different from the longitudinal wave, because in the longitudinal wave, notice as he sends a pulse of energy traveling through the slinky, again, the pulse of energy starts right here over on this end, and it travels all the way down to that end. So the pulses of energy are traveling like this. Pulses of energy in this case are traveling from right to left. Okay. Yeah. But guys, notice how he's vibrating his hands. In this particular case right here, he's vibrating his hand by pushing forward and backwards, pull forward and backwards, forward and backwards. So he pushes this way, and then he pulls back that way, and then he pushes this way again, pulls back that way again. So notice in this particular example here, notice how the vibrations are parallel to the direction that the wave itself is moving. So y'all see that? So I'm gonna say that again. So in a longitudinal wave, the vibrations act in the same direction that the wave is propagating. In other words, it's parallel to the direction of wave propagation. Okay. Remember, that is different from a transverse wave, because in the transverse wave, the vibrations are perpendicular to the direction of wave propagation. In this case, the direction his hand is vibrating is acting in another direction compared to the direction that the energy is traveling. So that's the difference between a transverse wave and a longitudinal wave. Okay, y'all got that? Okay. So going back to our worksheet. When I see you guys on next class period, we're going to get into a little bit more examples with different types of transverse waves and different types of longitudinal waves in nature. For now, you guys know the definition of these waves and how they will look like. Now, guys, there are some waves in nature that combine both types. For example, earthquakes. Earthquakes are made of both transverse and longitudinal waves. The transverse part of the waves are what does the most damage in an earthquake. Okay. But we're going to talk more about that on next time. Different types of longitudinal waves and different types of transverse waves. For now, guys, whenever you are modeling waves mathematically, it's important that you guys know a few terms, which is what I'm going to go over now. So, guys, typically whenever we're modeling waves mathematically, we typically draw graphs and draw waves out on a graph so that we can get a visualization of what's happening. Okay. Now, whenever you're modeling waves on a graph, here are the two terms. Here are the important terms you guys to know. Let's start with crest. Okay. So anytime you see a wave on a graph, guys, I need for you guys to know that the crest always represents the highest point on the wave. So the highest point on the wave, the very top, is considered a crest. So these dots here in red that I drew, those represents the crest. The troughs, on the other hand, the troughs will be the opposite. The troughs are the lowest point on the wave. They're at the bottom. These are our minimums. So these points here in blue, those represent our troughs. So these are crest and these are troughs. Okay, so those are some terms you guys need to know. Also, another term you guys need to know how to recognize the amplitude of a wave. Guys, it turns out the amplitude represents the height of the wave as measured from the midpoint. So, for example, look at this wave here. So, guys, notice here, this right here, hold on. This is the, this right here, this represents the midpoint of our wave, right? So that's the midpoint of our wave. In order to measure the amplitude, you need to measure the height of the wave from the midpoint to the highest point. So obviously this is the highest point of our wave. So guess what? That means, so guys, what that means is that this vertical distance from here to here, that is our amplitude. So the vertical distance from here to here is our amplitude. In this case right here, this amplitude tells us that this height here is 4 centimeters. So it's the height of the wave as measured from the midpoint. Of course, whenever you're measuring amplitude, there's two ways you can look at it. You can either measure the amplitude from the midpoint to the highest point, or you can measure the amplitude from the midpoint to the lowest point. So this distance here is the same thing as that distance here. So that's how you measure amplitude. Okay, so everybody got that? The amplitude is the height of the wave as as measured from the midpoint. One more term I need for you guys to know. I need for you guys to understand what is wavelength. What is wavelength? Well, guys, wavelength just represents the length of one cycle on the wave. So the way you measure wavelength, there's two ways you can measure wavelength. You can either measure wavelength from crest to crest, or you can measure wavelength from trough to trough. Okay, so for example, hold on, let me. Okay, so for example, if I want to measure the wavelength here, so notice here's one peak, here's another peak. So if I measure this is from crest. I measure this is from crest. Why is this not? Hold on, guys. I don't know why this is not. Okay. Come on. There we go. Okay. So if I measure this distance from crest to crest, this is considered to be my wavelength. In this case right here, notice this, the length of this wave right here is 1 meter long. So from here to here is 1 meter. So guys, you can either measure wavelength from crest to crest, or you can measure it from trough to trough. So you can do it from here to here. Both those distances are the same. Or guys, you can either measure it from the very first point of the wave to the end of one cycle. That's also the wavelength. But generally, most students like to do it from crest to crest or trough to trough. Okay, so the wavelength just represents the length of one cycle. Any questions before we do some of these example problems on the back? By the way, we're not going to talk about speed of a wave on today. We're going to talk more about that on next time. Today, I just wanted to cover some definitions just to be sure everybody's clear on this. All right, guys, let's look at this next page here. We're not going to do everything on this worksheet. I'm just going to do just enough so you guys can do the assignment by yourselves. Okay. All right, guys, let us look at the first section right here. Okay, so guys, on this first section right here, we're gonna be matching the correct number with the correct letter. Okay. So, guys, let's start with number 1. What letter goes to number 1? Anyone want to tell me in the chat box? What letter goes to number 1? Yes, it is A. Thank you, Jeremiah. What about number 2? Yep, it is D. Thank you, Angelina. Thank you, Jeremiah. Number 3, what letter goes to number 3? Yes, it is C. Number 4. Yep, it is B. And which means number 5, E. 5 has to be E. Wavelength represents the length for one cycle. All right. Hopefully that makes sense. Okay, let's move on. Let's look at this next section right here. So, yes or no? Do these situations right here represent wave motion? Now, guys, remember, in order to represent wave motion, you must have two components. Remember, waves combine harmonic motion and linear motion, right? Because so there must be something that repeats itself, and it also must be traveling along. Okay. So, FM radio, basically, guys, whenever they're talking about FM radio, they're talking about sound waves. Right? Radio waves are an example of a sound wave, and yes, sound waves, they do repeat themselves. There are waves that's oscillating in the atmosphere, and they propagate forward. So yes, this would be an example of wave motion. A car going at 70 meters per second. Now, guys, so if you just imagine a car just driving straight down the highway, and it's just traveling, in a straight line, this would not be an example of wave motion. Well, even though it has a linear component, it does not have a component that oscillates or repeats itself. There's no harmonic motion to a car going 70 meters per second down the highway. A clock pendulum. Okay. Now this one right here is kind of tricky. Okay. This one right here is tricky. And I'll tell you why it's tricky, because like if you think of a clock, like if you think one of those grandfather clocks that kind of sways back and forth like this. So while it does oscillate, so it does have a harmonic component to its motion. There's no linear component to its motion, like it's not traveling along. So this would be an example of no, right? Because in order to be wave motion, it has to have a harmonic component and a linear component to its motion. Ocean waves, we've already talked about this. Yes, because ocean waves travel. Obviously, they travel in the ocean, and of course, it involves some sort of oscillation. So, yes, that's an example of wave motion. Music. This is an example of sound waves. Yes, this is obviously an example of wave motion. A bulldozer. No, it's not an example of wave motion. Earthquakes. Yes, this would be an example of wave motion. And cell phones. And again, when I talk about cell phones, they're obviously talking about sound. So we're dealing with sound waves. So yes, this is an example of wave motion. Okay. And again, like I said, I'm not going to work out everything here. I just want to do enough for you guys to get the point. Let's go here. Let us look at these two questions right here, where it says a wave has a period of 4 seconds. Find its frequency. So guys, y'all tell me, if how do we find the frequency here? What do we do to find the frequency? Anybody? If we know the period, how do we find the frequency? If a wave.
Did you say like 1 divided by?
Yep. 1 divided by the period. Thank you, sir. So this case is going to be 1 divided by 4. 4. And what's 1 divided by 4? So 0.25 hertz. Okay. Remember, frequency is always in hertz. Yep. Thank you, Angelina. Anybody want to tell me right here? What's the answer here? If a wave has a frequency of 2 hertz, find its period. So could y'all tell me the answer and the units here?
Is that 0.5 hertz?
Not hertz. We're finding the period.
Oh, the period.
Do you remember the unit for period?
The answer
is right. It is 0.5. But it's 0.5 what?
Is it seconds?
Yes, sir. Thank you. 0.5 seconds. Hey guys, please remember that the unit for frequency is in hertz and the unit for period is in seconds. So remember that whenever you guys are working on that assignment. All right. The last thing I want to do today, I want to look at these last 3 graphs here. And basically, I just want to answer these last few questions here. Um, we're not going to answer everything. We're just going to answer just enough for you guys to get the point. So we have a graph here in which you have a wave represented on this graph. So this question says, how many wavelengths long is this graph? Well, let's count it, guys. In order to figure out how many wavelengths long is the graph, basically, you want to count the number of times the pattern repeats itself. So look closely here. Notice how so notice how the wave starts here, goes down like this, comes back up, and then by the time the line reaches this point right here, notice at that point right there, notice that's when the pattern starts to repeat itself. And so you guys should be able to see here that we have one wavelength represented right here, and then here we have another cycle that started, and this is another wavelength. So how many wavelength longs is this graph? Well, this graph here is 2 wavelengths long, so that's our answer, right? Because we have 2 cycles represented there. What is the length of one of those waves? In other words, what is the wavelength? Well, guys, look at the line that I drew in red. Okay, so if you look at your axis, it tells you your position in meters. So if you just look at one of those waves, the waves in red, notice right here, it reaches the end right here, right around 2 meters. So this wavelength is 2 meters long. So please include your units whenever you're talking about wavelength and amplitude. Now guys, how do we figure out the amplitude of this graph? Okay. Remember, guys, what amplitude is. Amplitude represents the height of the wave as measured from the midpoint. Okay, so first thing we need to do, we need to figure out the distance of the height of this wave from the top to the bottom. So in other words, the very first thing we're going to do, we're going to figure out the height of the wave from this point to that point, from top to bottom, right? So if you count the number of squares, 1, 2, 3, 4, 5, 6. So that means the length from top to bottom is 6 meters. So guess what that must mean? That must mean that our midpoint of this wave is somewhere around here. Okay. So if that's our midpoint, then it should be obvious to you guys that the distance from the midpoint to the highest point is 1, 2, 3 meters. So in this case right here, 3 meters is our amplitude. So everybody got that? That's what amplitude means. Amplitude represents the height of the wave as measured from the midpoint. Everybody got that? The height of the wave as measured from the midpoint. Okay. Let us look at these last 2 graphs here. We're not going to worry about finding the speed of the wave. We're not going to worry about that until next time. For now, I just want you guys to understand the various components of waves. So let's look at this graph right here. Again, I'm not going to answer everything. I just want to do enough for you guys to get the point. How many number of complete cycles do we have represented here? Well, guys, y'all should be able to look at this and figure out how many number of complete cycles we have represented here. Remember, guys, in order to count the number of cycles, you're basically looking for how many times the pattern itself repeats, right? Because, the cycle is going to be repeating itself over and over again. That's how we get waves. So let's look closely at this. So obviously from here to here, that represents 1 cycle. How do I know that represents 1 cycle? Because after that red line, notice how the picture begins to repeat itself. So notice how that blue line looks identical to the red line. So this is 1 cycle, 2 cycles, And then after that, we start to repeat ourselves again, and then 3 cycles, and then 4 cycles. So how many number of complete cycles do we have represented here? Well, we have 4 complete cycles. Yes, Angelina. We have 4 complete cycles, right? You just, in order to count the number of cycles, you just look for how many times the pattern is repeating itself. In other words, you're looking for the total number of wavelengths that is represented there. Okay, what exactly is the wavelength? Well, look at the bottom here. It tells us our position in meters. So, guys, look at the length of one of those cycles. So, guys, for example, look at that. Look at our line in red there. What is the length of that line from here to here? I can see that that's 1 meter. So the wavelength there is 1 meter. Now, you guys tell me, what is the amplitude here? I want you guys to tell me. I want you guys to look at that. Look at this graph here and tell me what the amplitude is. Y'all should be able to look at that and tell me. Anybody want to tell me in the chat box? Or if you want to unmute yourselves? Remember what amplitude is. It's the height of the wave that's measured from the midpoint. Come on, guys. The sooner y'all answer, the sooner we get done for the day. No, Anthony, the amplitude would not be 1. Look. Again, Anthony, go up higher. The amplitude is larger than 1. Yes, Christine, it is 2. Exactly. Thank you, Christine. The amplitude is 2 meters. Okay. Yeah. And see, and as you can see, notice this right here. That's the midpoint, right? That's the midpoint of our wave, and then this is the highest point. Yeah. Yeah, it's fine, Angelina. It's okay. So yeah, so you're measuring the height of the wave from the midpoint. Okay. All right, guys, here's the last one we're going to do, and then we're going to call it a day. By the way, can you guys just look at this and tell me how many number of complete cycles do we have represented here? For this graph, how many number of complete cycles do we have represented here?
Is it like 2.5, something like that?
No, it's not 2.5. It's 3. Exactly, it's 3. You were close, Jeremiah. Yes. So because look, notice here how so this right here represents 1 complete cycle, Jeremiah. And then after that, notice the pattern repeats itself. And after that, notice we get another cycle like this. Notice how the green line looks like the red line. And then after that, we get another cycle right here. So notice how the blue curve line looks like the green curve line, which looks like the red curve line. So how many number of complete cycles do we have represented here? We have 3 complete cycles. Makes sense, yeah. Right, so basically you're counting the number of times the pattern repeats itself. So 1 cycle, 2 cycle, and then 3 cycle. Okay, so we have 3 identical waves there. Now, what is the period here? Remember what period means. Period means the time for 1 cycle. Period means the time for 1 cycle. So if you guys notice here along the x-axis here, they actually have time measured in seconds. So guys, if you look at 1 cycle, so look at this curved line in red here. So if you look at 1 cycle from here to here, you look at 1 cycle, notice it takes 2 seconds to go 1 cycle. So I'm going to put my period is 2 seconds. So guys, if my period is 2 seconds, then that must means my frequency is equal to 1 divided by 2. So my frequency is equal to 0.5 hertz, right? Yeah, thank you, Angelina. Last one, can someone tell me what is the amplitude here of this wave here represented on this graph? Can someone tell me what is the amplitude there?
4.
Yes, 4, in this case, our units here is centimeters. So 4 centimeters. Okay, thank you, guys, because that's what amplitude is. Amplitude represents the height of the wave. All right, guys, any questions? Angelina, was that bad? Was that so bad today? See, I told you it's not going to be a lot of math. It wasn't too bad, was it? Awesome. Yeah, it wasn't too bad. If you guys understand everything today, you guys should be fine on the homework that is posted, um, or the work that I have posted in Schoology. Um, I'm going to in just a moment. I'm going to post a YouTube video in case you guys want to go back and look over that. Okay, so let me stop recording.